Right now, at this very moment, the foundation of modern cosmology is under siege by a growing body of evidence that challenges one of the most fundamental assumptions about our universe. Dark matter, the mysterious substance that supposedly comprises 85% of all matter in the cosmos, may not exist at all. After decades of searching with increasingly sophisticated detectors buried deep underground, orbiting in space, and smashing particles at the highest energies achievable by human technology, scientists have found absolutely nothing. Zero dark matter particles detected. Zero direct evidence for the substance that supposedly holds galaxies together and shapes the cosmic web itself. The absence of evidence is becoming evidence of absence. Leading physicists are now seriously considering that dark matter represents the most expensive wild goose chase in scientific history. A theoretical construct that seemed elegant on paper but bears no relationship to physical reality, instead of an exotic new form of matter filling the universe. The gravitational effects attributed to dark matter might result from our incomplete understanding of gravity itself, requiring modifications to Einstein's general relativity that could revolutionize physics. The crisis began with galaxy rotation curves measured by astronomer Vera Rubin in the 1970s. Which showed stars orbiting galactic centers at speeds that should tear galaxies apart according to visible matter calculations, rather than questioning our understanding of gravity. The scientific establishment invented an invisible substance 5 times more abundant than ordinary matter to explain these observations. This dark matter hypothesis became scientific orthodoxy despite never producing a single confirmed detection in over 4 decades of intensive searching. Recent observations have made the dark matter problem even worse. The James Webb Space Telescope has discovered massive, fully formed galaxies existing just 400 million years after the Big Bang, far too early for dark matter models to explain their formation. Computer simulations based on dark matter predict cosmic structures that differ dramatically from observations, requiring increasingly contrived explanations to maintain theoretical consistency. The mismatch between theory and observation grows more severe with each new generation of astronomical instruments. Alternative theories that modify gravitational physics rather than invoking invisible matter have successfully predicted many observations that surprised dark matter proponents. Modified Newtonian Dynamics MOND, proposed by physicist Mordechai Milgram in 1983, explains galaxy rotation curves, predicts the cosmic microwave background patterns, and accounts for gravitational lensing effects without requiring any dark matter whatsoever. Emergent gravity theories suggest that gravity itself arises from underlying quantum mechanical processes, naturally producing the effects attributed to dark matter. The Large Hadron Collider, the most powerful particle accelerator ever built, has failed to detect any of the theoretical particles proposed as dark matter candidates despite years of operation at energies that should have revealed their existence. Underground detectors using tons of ultra-pure materials shielded from cosmic radiation have recorded countless interactions but identified zero confirmed dark matter events. Space-based telescopes searching for dark matter annihilation signatures have found nothing beyond ordinary astrophysical processes. Meanwhile, precision measurements of gravitational effects in our solar system reveal tiny discrepancies from general relativistic predictions that could indicate modifications to gravitational physics. Operating at specific acceleration scales, these anomalies occur precisely at the acceleration regime where MOND theories predict departures from Newtonian behavior, suggesting that our understanding of gravity itself requires fundamental revision rather than invoking mysterious dark matter. The scientific method demands that theories be abandoned when they consistently fail to match observations and when simpler explanations become available. Dark matter theory requires the existence of an entirely new type of matter that interacts only gravitationally, comprises most of the universe's mass, but remains completely indetectable despite decades of searching with ever more sensitive instruments. Modified gravity theories require only adjusting our understanding of gravitational physics in regimes never previously tested. Galaxy collision observations, long cited as evidence for dark matter through the separation of ordinary matter from gravitational effects, can be explained equally well by modified gravity theories that predict similar phenomenology, without requiring invisible matter. The cosmic microwave background patterns used to constrain dark matter models also match predictions from alternative theories that modify gravitational physics rather than matter content. If you're fascinated by the possibility that one of science's most fundamental assumptions might be completely wrong, subscribe and hit the thumbs up button. What would it mean for our understanding of the universe if dark matter doesn't exist and gravity operates differently than we thought? Comment below, I'll pin the most insightful response. The implications of dark matter's non-existence extend far beyond cosmology to challenge the scientific process itself. How did an entire field become convinced of something that might not exist? What does this tell us about the relationship between theoretical elegance and empirical truth? The dark matter crisis reveals how scientific paradigms can persist long after evidence suggests they should be abandoned, maintained by institutional momentum rather than observational support. String theory, supersymmetry, and other exotic physics frameworks developed partly to provide dark matter candidates have produced no experimental confirmation despite consuming enormous research resources. These theoretical edifices, constructed on the assumption that dark matter exists, may represent decades of misdirected effort based on a fundamental misunderstanding of gravitational physics operating in galactic environments. The resolution of the dark matter crisis will likely require acknowledging that our understanding of gravity remains incomplete, particularly in regimes of extremely low acceleration where galactic dynamics operate, just as Newton's gravity required modification by Einstein's relativity for extreme velocities and masses. Einstein's theory may require modification for the extremely weak accelerations characteristic of galactic systems. Young physicists entering the field increasingly question dark matter orthodoxy, unencumbered by careers built on dark matter research and willing to consider alternatives that older generations find threatening to establish theoretical frameworks. This generational shift in perspective, combined with mounting observational evidence against dark matter's existence, suggests that a paradigm change in cosmology may be inevitable. The search for dark matter has driven remarkable technological advances in detector sensitivity, underground laboratories, and space-based observations that will benefit science regardless of whether dark matter exists. However, the opportunity cost of focusing exclusively on dark matter while neglecting alternative gravitational null theories may have delayed fundamental breakthroughs in understanding the universe's true nature. As we explore the mounting evidence against dark matter's existence and the alternative explanations that could revolutionize our understanding of gravity and cosmic structure, remember that science progresses by questioning fundamental assumptions and following evidence, wherever it leads, even when that means abandoning cherished theories that seemed elegant but proved incorrect. Now let's begin our investigation into why an increasing number of scientists believe dark matter represents the greatest theoretical mistake in modern physics. Starting with the observational crisis that threatens to topple one of cosmology's most fundamental assumptions. Detection failure. The most sophisticated particle detection experiments in human history have been searching for dark matter with increasing desperation for over 4 decades. Employing underground laboratories, space telescopes, and particle accelerators that represent billions of dollars in scientific investment. Despite this enormous effort using continuously improving technology, the result has been consistently the same: absolutely zero confirmed detections of dark matter particles. This systematic failure to find the substance that supposedly comprises 85% of all matter in the universe represents one of the most significant negative results in the history of experimental physics. Underground dark matter detectors operate in facilities carved deep into mountains and surrounded by thousands of tons of rock that shield experimental apparatus from cosmic radiation and other background interference. The Sanford Underground Research Facility in South Dakota houses multiple dark matter experiments, including the Lux Zeppelin detector, which uses 10 tons of liquid xenon cooled to -10 C and instrumented with thousands of photomultiplier tubes sensitive to individual photons of light that would be produced if dark matter particles collided with xenon nuclei. The theoretical basis for these underground experiments assumes that dark matter particles called WIMPs, weakly interacting massive particles, occasionally collide with ordinary matter nuclei, producing detectable energy signatures that can be distinguished from background radiation through sophisticated data analysis techniques. After years of operation with sensitivity reaching theoretical limits for many proposed dark matter candidates, these experiments have detected numerous particle interactions but identified exactly 0 confirmed dark matter events. The xenon collaboration, operating a series of increasingly sensitive liquid xenon detectors over 2 decades, has pushed the limits of dark matter detection sensitivity by orders of magnitude beyond initial expectations. The most recent XeNONT detector can identify individual nuclear recoils with energies as low as a few kiloelectron-volts, achieving background rejection ratios that exceed 1 part in 10 trillion. Despite this extraordinary sensitivity, the experiment continues finding only background events consistent with known radioactive processes. Space-based dark matter searches use gamma-ray telescopes to look for the characteristic radiation signatures that would be produced if dark matter particles annihilate with each other. In regions of high dark matter density, the Fermi Gamma-ray Space Telescope has surveyed the entire sky for over a decade, mapping gamma-ray sources with unprecedented precision and sensitivity. Theoretical models predict that dark matter annihilation should produce distinctive gamma-ray signatures from the galactic center and from dwarf satellite galaxies. But observations reveal only ordinary astrophysical sources. The Alpha Magnetic Spectrometer AMSO aboard the International Space Station has detected over 100 billion cosmic ray events during its operational lifetime, analyzing the energy spectra and composition of high-energy particles with precision that enables identification of exotic particle signatures that would indicate dark matter interactions. Despite theoretical predictions for specific dark matter signatures in cosmic ray spectra, AMSO measurements remain consistent with conventional astrophysical acceleration mechanisms without requiring dark matter explanations. Particle accelerator experiments at the Large Hadron Collider (LHC) have searched for dark matter through missing energy signatures that would indicate dark matter particle production in high-energy collisions between protons. The ATLAS and CMS detectors can identify energy momentum conservation violations that would occur if dark matter particles were created and escaped detection, but years of operation at the highest achievable collision energies have produced no evidence for dark matter particle creation. The theoretical parameter space for dark matter candidates has been systematically eliminated by these null results, forcing theorists to propose increasingly contrived scenarios to maintain dark matter viability. Early WIMP models predicted interaction cross-sections that should have been easily detectable with first-generation experiments. But continuous null results have pushed viable dark matter models toward interaction strength so weak that detection becomes practically impossible with any conceivable technology. Cryogenic dark matter detectors using superconducting quantum interference devices SQUIDs and transition edge sensors can measure temperature changes as small as microkelvin that would result from dark matter particle collisions with crystal lattices. The SuperSNS experiment uses germanium and silicon crystals cooled to millikelvin temperatures and surrounded by active veto systems that reject background events with extraordinary efficiency. Despite this sensitivity to individual phonon excitations in crystalline materials, no dark matter signatures have been confirmed. Directional dark matter detectors attempt to measure the recoil direction of nuclei struck by dark matter particles, which should show a preferred direction aligned with Earth's motion through the galactic dark matter halo. These experiments use low-pressure gas chambers where nuclear recoils create ionization tracks that can be imaged and analyzed to determine collision geometry. While the technology successfully demonstrates directional sensitivity, no dark matter signatures have been detected despite theoretical predictions for clear directional signals. The neutrino background represents an irreducible limitation for dark matter searches, as neutrinos from the Sun, atmosphere, and cosmic sources produce nuclear recoils that mimic dark matter signatures. As detector sensitivity approaches the neutrino floor, distinguishing dark matter signals from neutrino interactions becomes increasingly difficult, requiring larger detector masses and longer observation times that make experiments prohibitively expensive without providing corresponding increases in discovery potential. Axion dark matter. Searches use sensitive magnetometers and microwave cavities to detect the conversion of axions to photons in strong magnetic fields. Based on theoretical models that propose axions as alternative dark matter candidates with different interaction mechanisms than WIMPs. The Axion Dark Matter Experiment ADMX uses superconducting magnets and ultra-low noise amplifiers to achieve sensitivity approaching theoretical limits for axion photon coupling, but has detected no axion signals despite years of operation. Laboratory tests of the equivalence principle, which underlies general relativity, have achieved precision sufficient to detect violations that would be caused by dark matter interactions with ordinary matter. Experiments using torsion balances and atomic interferometry can measure gravitational effects with sensitivity exceeding 1 part in 1013, but have found no deviations from general relativistic predictions that would indicate dark matter's gravitational influence on laboratory scales, the absence of seasonal modulation signals in dark matter detectors contradicts theoretical predictions based on Earth's orbital motion through the galactic dark matter halo. As Earth orbits the Sun, its velocity relative to the dark matter halo should vary periodically, producing corresponding variations in dark matter interaction rates. Despite claims of annual modulation by some experiments, independent measurements using different detector technologies have failed to confirm these signals. Statistical analysis of dark matter search results reveals that the accumulated null results have reached significance levels that strongly disfavor many theoretical dark matter models. Bayesian analysis incorporating all experimental constraints shows that the probability of dark matter existing with properties compatible with cosmological observations has decreased dramatically. As detector sensitivity has improved without producing positive detections, alternative explanations for null dark matter results include the possibility that dark matter particles interact through forces other than those accessible to current detector technologies, that dark matter exists in forms that cannot be detected through nuclear recoils, or that dark matter models fundamentally misunderstand the nature of gravitational effects attributed to invisible matter. However, each alternative explanation requires increasingly exotic theoretical assumptions that reduce the elegance and predictive power that originally motivated dark matter hypothesis. The sociology of dark matter research reveals how experimental null results have been consistently reinterpreted to maintain theoretical viability rather than questioning fundamental assumptions. Each generation of more sensitive experiments that fails to detect dark matter is followed by proposals for even more sensitive future experiments, rather than consideration that dark matter might not exist at all. International coordination in dark matter research through organizations like the Dark Matter Working Group has standardized experimental techniques and data analysis methods, while simultaneously creating institutional momentum that discourages consideration of alternatives to dark matter hypothesis. The enormous financial and career investments in dark matter research create psychological barriers to acknowledging that decades of effort might have been misdirected. The opportunity cost of dark matter research includes resources that could have been devoted to testing alternative theories of gravity or investigating other unsolved problems in physics. While dark matter experiments have driven technological advances in detector sensitivity and background rejection, these advances might have been applied more productively to different research directions if the dark matter hypothesis had been questioned earlier. Future dark matter experiments propose even larger detectors with improved sensitivity, but fundamental limitations including neutrino backgrounds and theoretical parameter space constraints suggest negative results will continue regardless of technological improvements. The systematic failure to detect dark matter after 4 decades of increasingly sophisticated searching provides compelling evidence that the theoretical framework underlying these experiments may be fundamentally incorrect. Galaxy rotation crisis: the rotation curves of spiral galaxies, which measure how orbital velocity changes with distance from galactic centers, provided the original evidence for dark matter's existence but have become increasingly problematic for dark matter theory as observations reveal systematic patterns that contradict predictions from computer simulations based on invisible matter halos. These rotation curve anomalies, discovered by astronomer Vera Rubin and collaborators in the 1970s, showed that stars in galactic outer regions orbit much faster than expected from visible matter calculations, leading to the hypothesis that vast amounts of invisible dark matter must provide additional gravitational binding. Detailed analysis of galaxy rotation curves reveals that the discrepancy between observed velocities and those predicted from visible matter follows a precise mathematical relationship, known as the Bryonic-Tully-Fisher relation, which connects galactic mass to rotation velocity with remarkable accuracy across enormous ranges in galaxy size and brightness. This tight correlation suggests that whatever causes the rotation curve anomalies operates through a fundamental physical principle, rather than the random distribution of invisible matter halos predicted by dark matter models. High-resolution observations of individual galaxy rotation curves using radio interferometry and optical spectroscopy reveal fine structure details that challenge dark matter explanations while supporting alternative theories. The Milky Way's rotation curve shows features that correlate with visible spiral arms and bar structures in ways that suggest gravitational effects arise from baryonic matter distribution rather than from smooth dark matter halos that should not respond to stellar structure. The diversity of galaxy rotation curve shapes across different morphological types creates additional challenges for dark matter models, which predict universal rotation curve profiles determined by the physics of dark matter halo formation during cosmic structure assembly. Observations reveal systematic differences between early type and late type galaxies that correlate with stellar populations and star formation histories, rather than with the dark matter halo properties that supposedly dominate galactic dynamics. Computer simulations of galaxy formation within dark matter halos consistently predict rotation curves that differ from observations in systematic ways that have persisted despite decades of refinement in simulation techniques and theoretical understanding. The core-cusp problem, where simulations predict peak dark matter density profiles while observations favor flat central density cores, represents a fundamental mismatch between theory and observation that has resisted resolution. Low surface brightness galaxies, which contain proportionally more alleged dark matter relative to visible matter, provide crucial tests for dark matter theory through their extreme rotation curves that should be dominated by invisible matter effects. These galaxies exhibit rotation patterns that follow the same mathematical relationships observed in normal galaxies, suggesting that common physical principles govern all galactic dynamics regardless of the supposed dark matter content. The missing satellite problem describes the observation that the Milky Way contains far fewer satellite galaxies than predicted by dark matter simulations, which anticipate hundreds of dwarf satellites within the local group but observe only dozens. This discrepancy indicates that either dark matter simulations fundamentally misunderstand structure formation or that alternative explanations for galactic dynamics provide more accurate descriptions of cosmic structure, precision measurements of stellar kinematics in galactic outer regions using individual star velocities rather than average rotation curves reveal complex velocity dispersions and streaming motions that contradict the smooth gravitational potentials predicted by dark matter halos. These detailed kinematic studies suggest that galactic dynamics reflect complex baryonic physics rather than the relatively simple gravitational effects expected from dark matter dominance. The Fermi and Fermi to rotating disk instabilities predict that galaxies should develop bar structures and spiral patterns even without dark matter through purely gravitational interactions among stellar components. Observations of galaxy morphology evolution and the prevalence of barred spirals support these dynamical instability mechanisms while challenging the stabilizing influence that dark matter halos supposedly provide to galactic structure. Alternative gravitational theories, particularly Modified Newtonian Dynamics MOND, successfully predict galaxy rotation curves across the full range of observed galactic properties, using modifications to gravitational physics rather than invoking invisible matter. MOND's acceleration scale parameter, derived from galaxy rotation data, accurately predicts rotation curves for galaxies not used in the theory's development. demonstrating genuine predictive power that dark matter models lack. The acceleration scale where rotation curve anomalies become prominent corresponds to extremely weak gravitational fields that were never tested in solar system experiments that confirm general relativity. This suggests that Einstein's gravitational theory, while accurate for strong fields, may require modification in the ultra-weak acceleration regime characteristic of galactic outskirts where rotation curve anomalies occur, gravitational lensing observations that are often cited as independent evidence for dark matter can be explained equally well by modified gravity theories that predict enhanced gravitational effects in weak acceleration regimes. The lensing strength observed in galaxy clusters and individual galaxies matches predictions from modified gravity without requiring any invisible matter component. The radial acceleration relation RAR discovered through precise analysis of galaxy rotation data reveals a tight correlation between gravitational acceleration from visible matter and total observed acceleration that holds across all galactic environments. This fundamental relationship suggests that galactic dynamics are determined entirely by visible matter distribution through modified gravitational physics, rather than by the random dark matter distributions predicted by cosmological simulations. Dwarf galaxy rotation curves provide particularly stringent tests of dark matter theory because these small galaxies allegedly contain the highest dark matter fractions, and should therefore show the clearest dark matter signatures. However, dwarf galaxy dynamics follow the same acceleration relationships observed in larger galaxies, indicating that universal gravitational modifications explain all galactic rotation phenomena without requiring invisible matter. The too big to fail problem describes massive dark matter subhalos in cosmological simulations that should host bright satellite galaxies but are not observed around the Milky Way or Andromeda. This discrepancy suggests that either dark matter simulations fundamentally misunderstand structure formation or that the entire dark matter framework provides an inadequate description of cosmic structure evolution. Stellar archaeology studies of galactic chemical evolution reveal abundance patterns that reflect star formation and stellar nucleosynthesis processes, without requiring dark matter influences on galactic assembly. To observe correlations between stellar metallicity, kinematics, and spatial distribution reflect baryonic physics operating in gravitational potentials determined by visible matter rather than dark matter domination. The timing problem in galaxy formation describes the observation that galaxies appear fully assembled at very early cosmic epochs, inconsistent with the hierarchical assembly predicted by dark matter models where large galaxies form through mergers of smaller systems over cosmic time. Early galaxy observations by the James Webb Space Telescope exacerbate this timing problem by revealing massive, mature galaxies existing earlier than dark matter models can explain. Gas dynamics in galaxy outer regions, traced through neutral hydrogen observations, reveal systematic patterns in gas velocity and distribution that correlate with stellar structure rather than with dark matter distributions predicted by cosmological simulations. These gas kinematic studies provide independent confirmation that galactic dynamics are determined primarily by baryonic matter. Through modified gravitational physics, the universal acceleration scale characteristic of galaxy rotation anomalies suggests a fundamental physical constant related to gravitational modifications rather than the environmental variations expected if rotation curves resulted from diverse dark matter halo properties. This universality indicates that galaxy rotation reflects intrinsic gravitational physics rather than extrinsic dark matter influences. Comparative studies of galaxy rotation curves across cosmic time using observations of distant galaxies reveal evolution patterns that contradict dark matter predictions. While supporting modified gravity scenarios, the observed evolution in rotation curve shapes and the baryonic-Tully-Fisher relation reflects changes in galactic stellar populations and gas content, rather than the dark matter halo evolution predicted by cosmological models. Laboratory tests of gravitational physics at the acceleration scales characteristic of galaxy rotation anomalies remain technically challenging, but increasingly feasible with advancing precision measurement techniques. Future experiments using torsion balances, atom interferometry, and space-based platforms may directly test whether gravitational modifications predicted by alternative theories actually operate at galactic acceleration scales. The systematic failure of dark matter models to predict observed galaxy rotation curve properties across all galactic types and environments provides compelling evidence that galactic dynamics result from modifications to gravitational physics rather than from invisible matter that has somehow evaded detection despite 40 years of intensive searching using increasingly sophisticated experimental techniques and theoretical frameworks. Simulation problems. Computer simulations of cosmic structure formation based on dark matter models have consistently failed to reproduce key observational features of galaxies and cosmic structure, creating systematic discrepancies that have persisted and worsened as both simulations and observations have become more sophisticated. These failures span multiple scales from individual galaxy properties to large-scale structure statistics, suggesting that the underlying dark matter framework provides an inadequate description of how gravitational physics operates in cosmic environments. The core-cusp problem represents perhaps the most persistent failure of dark matter simulations, where predicted density profiles for dark matter halos show sharp central peaks while observations of galaxy rotation curves indicate flat central density cores. Decades of simulation refinement incorporating stellar feedback, supernova explosions, and active galactic nucleus effects have failed to resolve this fundamental mismatch, suggesting that the problem lies in the dark matter assumption itself rather than in incomplete simulation physics. Dark matter-only simulations predict cosmic web structures that differ systematically from observations, with too much power on small scales and insufficient correlation between galaxy properties and our large-scale environment. The Millennium simulation and its successors predict thousands of massive subhalos within galaxy-sized dark matter halos. But observations reveal only dozens of satellite galaxies around massive systems like the Milky Way and Andromeda. Hydrodynamic simulations that include baryonic physics alongside dark matter show improvement in some areas but require extensive parameter tuning and feedback mechanisms to approximate observed galaxy properties. The Illustristing Project and AGLE simulations achieve reasonable agreement with certain observational statistics only through carefully calibrated stellar feedback models that effectively suppress the effects of dark matter on galactic scales. The diversity problem in dark matter simulations describes the prediction that galaxy rotation curves should show much greater variety than observed, with some galaxies expected to show rising rotation curves, others flat curves, and still others declining curves depending on their dark matter halo concentration. Observations reveal that essentially all galaxies follow similar rotation curve shapes that correlate with stellar mass rather than with dark matter halo properties. Predicted galaxy formation timescales in dark matter simulations consistently exceed observational constraints, particularly for massive galaxies observed at high redshifts by telescopes like the James Webb Space Telescope. Dark matter models predict hierarchical assembly where large galaxies form through mergers of smaller systems over cosmic time, but observations reveal massive, mature galaxies existing much earlier than simulations can explain. The satellite galaxy orbital decay problem occurs in dark matter simulations where dynamical friction causes satellite galaxies to spiral into central galaxies much faster than observed. The Magellanic Clouds should have merged with the Milky Way billions of years ago according to dark matter simulations, but they remain in stable orbits that suggest either dark matter halos have different properties than predicted or that alternative gravitational physics affects satellite dynamics. Small-scale structure statistics from dark matter simulations predict matter clustering patterns that disagree with observations on scales below several megaparsecs. The Lyman alpha forest, which traces matter distribution through its effect on background quasar spectra, shows less power on small scales than predicted by dark matter models, suggesting that structure formation proceeds differently than assumed in standard cosmological frameworks. Velocity distribution functions in dark matter simulations predict that galaxy peculiar velocities should show broader dispersions than observed, with more galaxies exhibiting high velocities relative to cosmic expansion. The observed narrower Velocity distributions suggest that cosmic structure formation involves physical processes not captured by dark matter models, possibly including modifications to gravitational physics that affect large-scale dynamics. The angular momentum problem in galaxy formation simulations describes the systematic underprediction of galactic disk angular momentum compared to observations. Dark matter halos in simulations transfer angular momentum less efficiently than required to explain observed galaxy properties, necessitating complex baryonic feedback mechanisms that effectively circumvent dark matter physics. To achieve realistic galaxy formation, morphological diversity in galaxy populations predicted by dark matter simulations differs from observations in systematic ways, with simulations producing too many early-type galaxies and too few late-type spiral systems. The predicted correlations between galaxy morphology and environment also disagree with observations, suggesting that galaxy formation physics differs fundamentally from dark matter-based theoretical expectations. Galaxy clustering statistics on intermediate scales reveal discrepancies between dark matter predictions and observations that have been termed the sigmoid tension. Different observational probes yield inconsistent values for the amplitude of matter clustering when interpreted through dark matter models, suggesting that these models inadequately describe structure formation across multiple scales. The void statistics problem describes observations that cosmic voids contain fewer galaxies and show different size distributions than predicted by dark matter simulations. Voids in dark matter models should be populated by numerous faint galaxies associated with small dark matter halos. But observations reveal emptier voids that suggest structure formation operates differently than assumed in standard models. Baryonic physics implementations in dark matter simulations require increasingly complex feedback mechanisms to suppress structure formation on galactic scales, where dark matter effects should dominate. Stellar winds, supernovae, and active galactic nuclei must operate with precisely tuned efficiencies to counteract dark matter clustering, suggesting that baryonic physics fundamentally alters predictions in ways that undermine dark matter's explanatory power. The missing baryons problem in cosmic structure simulations describes the observation that galaxy groups and clusters contain less ordinary matter than predicted by cosmic abundance measurements. Dark matter simulations predict that most baryons should accumulate in gravitational potential wells, but observations reveal that much of the predicted ordinary matter remains undetected in any form. Scale-dependent bias in galaxy clustering reveals that the relationship between galaxy distribution and underlying matter distribution varies with spatial scale in ways not predicted by dark matter models. These scale dependencies suggest that galaxy formation involves physical processes that fundamentally alter the predicted relationship between visible galaxies and dark matter halo properties. The cuspy halo problem extends beyond individual galaxies to galaxy groups and clusters, where dark matter simulations predict central density profiles that conflict with gravitational lensing. Observe it. Ions. Cluster scale strong lensing requires smoother central mass distributions than predicted by dark matter-only simulations, necessitating additional physics to explain observational constraints. Computational convergence. Studies reveal that dark matter simulation results continue changing as resolution improves, indicating that fundamental physics may be missing from the theoretical framework rather than merely requiring better numerical techniques. The persistent dependence of results on simulation parameters suggests systematic problems with the underlying dark matter assumptions. Alternative gravity simulations that modify gravitational physics instead of invoking dark matter successfully reproduce many observational features that challenge dark matter models. Modified Newtonian Dynamics MOND simulations predict galaxy rotation curves, cosmic microwave background patterns, and large-scale structure statistics without requiring invisible matter components that remain undetected despite extensive searching. Machine learning analysis of simulation outputs reveals systematic patterns in the discrepancies between dark matter predictions and observations, with neural networks identifying correlations that suggest missing physics in the theoretical framework. These algorithmic approaches provide model-independent evidence that dark matter simulations fail to capture essential aspects of cosmic structure formation. The fine-tuning required to make dark matter simulations match observations has reached levels that undermine the theoretical elegance originally motivating dark matter hypothesis. The numerous free parameters in feedback models, the precise calibration required for Bryonic physics, and the ad hoc mechanisms needed to suppress dark matter effects suggest that the fundamental theoretical framework may be incorrect. Future simulation projects propose even higher resolution and more complex physics modules, but the persistent failures across multiple observational tests suggest that computational improvements alone cannot resolve the systematic discrepancies between dark matter predictions and cosmic structure observations. The accumulated evidence indicates that alternative theoretical frameworks may be required to understand cosmic structure formation. The comparison between simulation predictions made before observational campaigns and the subsequent observations reveals consistent patterns where dark matter models fail to anticipate observed phenomena. This predictive failure contrasts with successful scientific theories that anticipate observations before they are made, suggesting that dark matter theory lacks the empirical foundation required for reliable theoretical framework. Alternative theories Modified Newtonian Dynamics MOND, proposed by physicist Mordechai Milgram in 1983, represents the most successful alternative to dark matter by modifying gravitational physics at extremely low accelerations rather than invoking invisible matter to explain galactic dynamics. MOND introduces a fundamental acceleration scale below which gravitational physics deviates from Newton's inverse square law, creating enhanced gravitational effects that successfully predict galaxy rotation curves without requiring any dark matter component. The theoretical foundation of MOND rests on the observation that galaxy rotation anomalies occur consistently at accelerations around 1.2 times 10 to 10 meters per second squared, a value that appears universal across all galactic systems regardless of their size, mass, or morphology. This acceleration scale suggests a fundamental physical constant related to gravitational modifications rather than the environmental effects expected if rotation anomalies resulted from variable dark matter distributions. Emergent gravity theories propose that gravitational physics arises from underlying quantum mechanical processes in ways that naturally produce modifications at low acceleration scales, without requiring exotic matter components. These approaches suggest that gravity emerges from quantum entanglement between degrees of freedom associated with matter and spacetime, creating deviations from Einstein's general relativity in regimes where quantum effects become significant for macroscopic gravitational phenomena. FR gravity models modify Einstein's field equations by replacing the Ricci scalar with arbitrary functions of curvature, enabling gravitational modifications that can explain cosmic acceleration and galactic dynamics. Without dark matter or dark energy, these theories predict specific signatures in gravitational wave observations and precision tests of gravitational physics that could distinguish modified gravity from general relativity plus invisible matter components. Extra-dimensional gravity theories suggest that apparent dark matter effects result from gravitational interactions with additional spatial dimensions beyond the 3 dimensions of ordinary space. In these models, gravity can leak into extra dimensions at large distances, effectively weakening gravitational binding in galactic systems and requiring modifications to standard gravitational calculations to account for higher dimensional effects. Scalar tensor gravity theories incorporate additional scalar fields alongside Einstein's tensor gravitational field, creating modifications to gravitational physics that depend on local matter density and acceleration scales. These theories can produce dark matter-like effects in galactic environments, while maintaining agreement with solar system tests of general relativity through screening mechanisms that suppress scalar field effects in high-density regions. Vector tensor gravity models introduce vector fields that couple to matter and gravity, creating preferred directions in spacetime that can explain cosmological observations including galaxy rotation CRVs, and cosmic microwave background patterns. These theories predict specific polarization signatures in gravitational wave observations that could provide empirical tests distinguishing vector tensor gravity from general relativity. Biometric gravity theories propose that gravitational physics involves two different metric tensors describing spacetime geometry, with ordinary matter coupling primarily to one metric while gravitational effects involve both metrics through interaction terms. These models can explain cosmic acceleration and galactic dynamics through the interplay between different gravitational sectors without requiring dark matter or dark energy components. Non-local gravity modifications introduce spatial and temporal derivatives beyond second order into gravitational field equations, creating long-range gravitational effects that can explain dark matter phenomena through purely gravitational mechanisms. These theories predict specific signatures in cosmic structure formation and gravitational wave propagation that differ from general relativity plus dark matter models. Quantum gravity phenomenology suggests that dark matter effects arise from quantum mechanical corrections to classical general relativity that become significant in weak gravitational fields, characteristic of galactic environments. These approaches connect fundamental quantum gravity research with observational cosmology by predicting specific modifications to gravitational physics at cosmological scales. The conformal gravity theory proposed by Philip Mannheim modifies gravitational physics through conformal symmetry principles that naturally explain galaxy rotation curves and cosmic acceleration. Without dark matter or dark energy, this theory makes specific predictions for gravitational effects in binary pulsar systems and gravitational wave observations that can be tested against general relativistic expectations. Holographic dark matter models propose that apparent dark matter effects arise from information theoretic constraints imposed by black hole thermodynamics and the holographic principle, suggesting that gravitational modifications emerge naturally from fundamental limits on information processing in gravitational systems. These approaches connect cosmology with quantum information theory and black hole physics. Analog gravity models study gravitational phenomena using condensed matter systems that exhibit similar mathematical structure to general relativity, providing laboratory tests for modified gravity theories and insights into how quantum mechanical systems can exhibit gravitational-like collective behavior. These analog systems demonstrate that apparent dark matter effects can arise from purely classical physics in appropriate parameter regimes. Self-interacting gravity theories propose that gravitational fields interact with themselves in ways beyond those predicted by general relativity, creating nonlinear effects that can explain cosmic structure formation and galactic dynamics. These theories predict specific signatures in strong gravitational fields around black holes and neutron stars that differ from general relativistic expectations. Massive gravity models modify general relativity by giving the graviton a small but non-zero mass, creating modifications to gravitational physics on cosmological scales that can explain cosmic acceleration and potentially galactic dynamics without requiring dark components. These theories predict specific dispersion relations for gravitational waves that could be tested with future detector networks. Entropic gravity approaches suggest that gravitational physics emerges from thermodynamic principles operating on cosmological scales, naturally producing modifications that explain dark matter and dark energy phenomena through entropy considerations. These theories connect gravitational physics with statistical mechanics and information theory in ways that could revolutionize understanding of spacetime and matter. Causal sets theory proposes that spacetime consists of discrete causal structures rather than continuous manifolds, creating modifications to gravitational physics on large scales that could explain cosmic observations without dark components. This approach connects quantum gravity research with observational cosmology through specific predictions for cosmic structure formation and evolution. Asymptotic safety scenarios for quantum gravity suggest that gravitational physics becomes scale invariant at large distances, creating modifications that naturally explain cosmic acceleration and potentially galactic dynamics through running gravitational coupling constants that vary with energy scale. These approaches predict specific signatures in cosmic microwave background observations and large-scale structure. Loop quantum gravity modifications to general relativity predict discrete spacetime structure that creates deviations from classical gravitational physics on cosmological scales. These modifications could explain cosmic acceleration and galactic dynamics through quantum geometric effects that become significant in weak gravitational fields characteristic of cosmic structure. The rainbow gravity approach modifies dispersion relations for particles and gravitational waves in ways that depend on energy, creating effective modifications to gravitational physics that could explain cosmic observations without dark components. These theories predict specific signatures in high-energy astrophysical observations and gravitational wave astronomy. Dimensional reduction models propose that effective gravitational physics in 3 spatial dimensions differs from 4-dimensional general relativity due to compactification effects from extra dimensions, creating modifications that can explain galactic dynamics and cosmic acceleration through geometric effects rather than exotic matter components. Non-commutative geometry approaches to gravity introduce mathematical structures where coordinates do not commute, creating modifications to gravitational physics that could explain cosmic observations through purely geometric effects. These theories connect fundamental mathematical physics with observational cosmology in ways that could provide alternatives to dark matter paradigms. The success of alternative gravity theories in explaining multiple observational phenomena without requiring undetected matter components suggests that modifications to gravitational physics provide more elegant and empirically successful explanations for cosmic structure than dark matter hypotheses. These theoretical frameworks make testable predictions that distinguish them from general relativity plus dark matter, enabling empirical evaluation of competing paradigms. Quantum foundations. The quantum mechanical foundations underlying gravitational physics remain incompletely understood, with growing evidence suggesting that dark matter effects might arise from quantum corrections to classical general relativity rather than from exotic matter particles that have somehow evaded detection despite intensive searches. Recent developments in quantum gravity research reveal that gravitational physics involves quantum mechanical phenomena that become significant in weak field regimes, characteristic of galactic dynamics, potentially explaining observed gravitational anomalies through purely quantum effects. Quantum field theory in curved spacetime predicts that vacuum fluctuations respond differently to gravitational fields than anticipated by classical general relativity, creating effective stress-energy contributions that modify gravitational dynamics in regions of low acceleration. These quantum corrections could naturally produce the enhanced gravitational effects attributed to dark matter without requiring any new matter components, suggesting that dark matter represents a misinterpretation of quantum gravitational phenomena. The holographic principle, derived from black hole thermodynamics and string theory, implies that gravitational physics in any volume of space can be completely described by information encoded on the boundary of that volume. This principle suggests that gravitational effects in galactic systems might be determined by quantum information processing on cosmic horizons, rather than by matter distribution within galactic volumes, potentially explaining dark matter phenomena through information-theoretic constraints. Entanglement-based gravity theories propose that gravitational attraction arises from quantum entanglement between matter and space-time degrees of freedom, creating modifications to gravitational physics that depend on entanglement structure rather than purely on matter distribution. These approaches predict specific deviations from general relativity in weak field regimes that could explain galactic rotation curves through quantum mechanical rather than classical gravitational effects, vacuum birefringence, and other quantum electrodynamic phenomena demonstrate that electromagnetic fields experience quantum corrections in strong field regimes, suggesting analogous quantum gravitational corrections could affect gravitational fields in appropriate parameter regimes. Laboratory measurements of quantum electromagnetic effects in intense laser fields provide experimental precedents for quantum corrections to classical field theories that could extend to gravitational physics. The cosmological constant problem reveals a fundamental discord between quantum field theory predictions for vacuum energy density and observational constraints from cosmic expansion, suggesting that quantum mechanical contributions to gravitational physics remain poorly understood. Resolution of this problem might require quantum gravitational effects that naturally regulate vacuum contributions to cosmic dynamics, while producing observable modifications to galactic gravitational physics. Zero-point energy. Fluctuations in quantum field theory create stress energy distributions that couple to gravitational fields according to Einstein's field equations. But the magnitude and spatial distribution of these quantum effects remain uncertain due to renormalization ambiguities and the absence of a complete quantum theory of gravity. These quantum contributions could potentially explain gravitational anomalies attributed to dark matter, quantum corrections to black hole physics, including Hawking radiation, and quantum information preservation mechanisms. Demonstrate that gravitational phenomena involve quantum mechanical processes that modify classical general relativistic predictions. Similar quantum effects operating in galactic environments could create gravitational modifications that explain rotation curve anomalies without requiring invisible matter components. The measurement problem in quantum mechanics intersects with gravitational physics through proposals that gravitational effects cause quantum wave function collapse, creating feedback mechanisms between quantum mechanical systems and spacetime geometry that could modify gravitational dynamics in ways not captured by classical general relativity. These quantum gravitational interactions might naturally produce dark matter-like effects. Quantum spacetime fluctuations at the Planck scale create uncertainties in gravitational field measurements that accumulate over cosmic distances and time scales, potentially creating systematic modifications to gravitational physics in weak field regimes. These accumulated quantum effects could explain galactic dynamics without requiring dark matter if quantum gravitational phenomena operate differently than anticipated by semi-classical approximations. Spontaneous symmetry breaking in quantum field theory provides mechanisms for generating effective gravitational modifications through phase transitions that create preferred directions or scales in spacetime geometry. These symmetry-breaking mechanisms could naturally produce the acceleration scale observed in galactic rotation anomalies through quantum field theoretical processes, rather than exotic matter interactions. The DS-CFT correspondence and other holographic dualities demonstrate deep connections between gravitational physics and quantum field theory in lower-dimensional systems, suggesting that gravitational phenomena might emerge from underlying quantum mechanical degrees of freedom in ways that fundamentally modify expectations from classical general relativity. These emergent gravity scenarios could explain dark matter effects through quantum mechanical origins. Quantum gravity phenomenology predicts specific signatures of quantum spacetime structure that become observable in appropriate experimental regimes, including modifications to gravitational propagation and coupling that could affect galactic dynamics. Laboratory tests using precision gravimeters and torsion balances approach sensitivity levels where quantum gravitational effects might become detectable. Loop quantum gravity and other discrete spacetime approaches predict that gravitational physics involves fundamental discreteness at microscopic scales. That creates effective modifications to macroscopic gravitational dynamics through collective quantum effects. These discrete quantum gravity effects could accumulate over galactic scales to produce gravitational anomalies that mimic dark matter without requiring exotic matter components. Causal dynamical triangulation and other computational approaches to quantum gravity demonstrate that quantum spacetime fluctuations create effective modifications to classical gravitational physics through emergent geometric properties that differ from smooth manifold assumptions underlying general relativity. These quantum geometric effects could explain cosmic structure formation without dark matter. The black hole information paradox reveals fundamental tensions between quantum mechanics and general relativity that might require modifications to gravitational physics operating in regimes where quantum effects become significant for macroscopic gravitational phenomena. Resolution of this paradox could provide insights into quantum gravitational effects that explain galactic dynamics. Quantum error correction mechanisms proposed for preserving information in black hole evaporation could extend to cosmic structure formation, creating effective modifications to gravitational dynamics through quantum information processing constraints that operate on galactic scales. These quantum information effects might naturally produce gravitational anomalies attributed to dark matter. The firewall paradox and other quantum gravity puzzles suggest that gravitational physics involves quantum mechanical phenomena that fundamentally alter classical expectations. For spacetime structure and gravitational dynamics, these quantum gravitational effects could create observable modifications to galactic physics without requiring exotic matter components or modifications to general relativity. Emergent spacetime scenarios propose that gravitational physics arises from underlying quantum mechanical systems in ways that naturally produce modifications to classical general relativity. Through collective quantum effects, these emergent gravity theories predict specific signatures in weak field regimes that could explain galactic rotation curves through quantum mechanical rather than classical gravitational mechanisms. Quantum simulator experiments using ultra-cold atomic gases and other controllable quantum systems demonstrate that quantum many-body systems can exhibit collective behavior that mimics gravitational phenomena, providing laboratory analogies for how quantum effects might modify gravitational physics in cosmic environments. These analog gravity systems offer insights into quantum gravitational mechanisms that could explain dark matter effects. The quantum-to-classical transition in gravitational physics remains poorly understood, with growing evidence suggesting that quantum effects might persist to macroscopic scales in weak gravitational fields characteristic of galactic environments. Understanding this transition could reveal quantum gravitational effects that explain cosmic structure formation without requiring dark matter components. Precision tests of quantum gravitational effects using atomic interferometry and other quantum sensing technologies approach sensitivity levels where quantum corrections to classical general relativity might become detectable in laboratory settings. These experiments could provide direct empirical evidence for quantum gravitational phenomena that naturally explain galactic dynamics through quantum mechanical rather than exotic matter mechanisms. The integration of quantum mechanics with gravitational physics through various quantum gravity approaches consistently suggests that gravitational phenomena involve quantum mechanical processes that modify classical expectations in ways that could naturally explain cosmic structure formation and galactic dynamics without requiring dark matter or other exotic components beyond the standard model of particle physics. Observational anomalies. Precision astronomical observations have revealed systematic patterns in cosmic structure that consistently contradict dark matter predictions while supporting alternative theories that modify gravitational physics rather than invoking invisible matter. These observational anomalies span multiple scales from planetary system dynamics to cosmic Webb statistics, creating a comprehensive picture of gravitational effects that cannot be explained through dark matter models regardless of parameter adjustments or theoretical refinements. The Pioneer anomaly, discovered through precise radio tracking of the Pioneer 10 and 11 spacecraft as they traveled beyond the outer solar system, revealed unexplained acceleration toward the Sun that could not be accounted for by known forces, including solar radiation pressure, gravitational effects from known bodies, or spacecraft systematics. While later analysis attributed this acceleration to thermal effects, the precision required to identify these subtle influences demonstrates the sensitivity needed to detect gravitational modification at weak acceleration scales. Anomalous perihelion precession of planetary orbits provides potential signatures of gravitational modifications operating within the solar system, with recent measurements using radar ranging and spacecraft tracking achieving precision sufficient to detect deviations from general relativistic predictions at the level where modified gravity theories predict observable effects. These measurements constrain theoretical models while potentially revealing gravitational physics beyond Einstein's theory. The flyby anomaly affects spacecraft trajectories during Earth gravity assists, creating unexpected velocity changes that correlate with flyby geometry in ways that suggest systematic gravitational effects beyond those predicted by general relativity. Multiple spacecraft including Galileo, Near, Cassini, and Rosetta have exhibited these anomalous velocity changes. indicating either unknown systematic effects or genuine modifications to gravitational physics. Operating at specific acceleration scales. Galactic plane alignment problems reveal that satellite galaxy orbital planes show correlations with cosmic web structure that contradict dark matter simulations predicting random satellite orientations within isotropic dark matter halos. The observed correlations suggest that galactic dynamics respond to large-scale structure in ways that modified gravity theories predict but dark matter models cannot explain, without invoking highly contrived initial conditions. Cosmic microwave background polarization patterns contain information about gravitational physics during cosmic recombination that can distinguish between dark matter models and modified gravity theories. Recent measurements by the Planck satellite reveal subtle anomalies in polarization statistics that challenge standard cosmological models while remaining consistent with modified gravity approaches that naturally explain structure formation without dark matter. The void phenomenon describes regions of space with significantly lower galaxy density than predicted by dark matter simulations, suggesting that structure formation operates through gravitational mechanisms not captured by standard models. These cosmic voids show internal structure and galaxy populations that correlate with modified gravity predictions while challenging dark matter-based theoretical expectations for void properties. Weak gravitational lensing surveys reveal systematic patterns in cosmic structure that differ from dark matter predictions, with observed lensing statistics showing correlations between galaxy properties and gravitational effects that suggest modifications to gravitational physics rather than invisible matter distributions. These lensing observations provide model-independent tests of gravitational theories across cosmic scales. The Hubble tension describes systematic discrepancies between measurements of cosmic expansion rate using different observational methods, with local measurements yielding higher values than inferred from cosmic microwave background observations assuming standard cosmological models. This tension might indicate systematic problems with dark matter and dark energy assumptions rather than merely observational uncertainties. Timing variations in binary pulsar systems provide the most precise tests of gravitational physics available, with measurements achieving sensitivity to gravitational effects at levels approaching fundamental theoretical limits. Recent pulsar timing observations reveal subtle anomalies that could indicate gravitational modifications beyond general relativity. Though these effects remain at the limits of current measurement precision, the galaxy void cross-correlation statistics reveal spatial relationships between galaxies and cosmic voids that contradict dark matter simulation predictions, while matching modified gravity expectations for how matter responds to large-scale gravitational modifications. These cross-correlations provide sensitive tests of gravitational theories that are independent of galaxy formation physics uncertainties. Redshift space distortion patterns in galaxy surveys measure how peculiar velocities modify observed galaxy clustering statistics, providing direct tests of gravitational growth of cosmic structure. Recent measurements reveal systematic deviations from dark matter predictions that could indicate modifications to gravitational physics operating on cosmic scales rather than merely baryonic feedback effects. The cosmic web itself shows filamentary structure with properties that challenge dark matter models while supporting modified gravity theories that predict enhanced structure formation through gravitational modifications. The observed correlations between galaxy properties and cosmic web environments suggest that gravitational physics operates differently than assumed in standard cosmological models. Local group dynamics reveal systematic patterns in satellite galaxy kinematics that contradict dark matter expectations while supporting modified gravity predictions for how gravitational effects operate in galaxy group environments. The observed velocity dispersions and spatial correlations among local group galaxies suggest gravitational modifications rather than dark matter dominance. Gravitational wave observations by LIGO and Virgo provide new tests of gravitational physics in strong field regimes that complement weak field tests from galactic dynamics, while current gravitational wave observations remain consistent with general relativity Future observations with improved sensitivity might reveal modifications that connect strong field and weak field. Degravitational physics. The Borean acoustic oscillation scale measured in galaxy surveys provides a standard ruler for cosmic distances that can test gravitational theories through their predictions for cosmic expansion and structure formation. Recent measurements reveal subtle systematic effects that could indicate modifications to gravitational physics rather than merely dark energy effects. Surface brightness fluctuation measurements in galaxy clusters reveal mass distributions that differ systematically from dark matter predictions while remaining consistent with modified gravity expectations for how gravitational effects operate in cluster environments. These observations provide independent tests of gravitational theories that avoid uncertainties associated with galaxy formation physics. The integrated Sachs-Wolf effect creates correlations between cosmic microwave background temperature fluctuations and large-scale structure that depend on gravitational physics. Operating during cosmic evolution, measurements of this effect reveal patterns that challenge dark matter models while supporting modified gravity approaches to cosmic structure formation. Galaxy morphology statistics show systematic correlations between galaxy shapes and their cosmic environment that contradict dark matter simulation predictions, while matching modified gravity expectations for how gravitational modifications affect galaxy formation. These morphological studies provide additional evidence for gravitational physics beyond standard models. The cosmic velocity field map through peculiar velocity surveys reveals large-scale flows of galaxies that differ from dark matter predictions while matching modified gravity expectations for how gravitational modifications affect cosmic dynamics. These velocity measurements provide direct tests of gravitational theories through their predictions for cosmic structure growth. Type Ia supernovae observations that revealed cosmic acceleration might indicate modifications to gravitational physics rather than dark energy if systematic effects in supernova standardization correlate with gravitational modifications predicted by alternative theories. Recent analyses of supernova data reveal subtle systematics that could support modified gravity interpretations. Gravitational time delay measurements using strong gravitational lensing provide tests of gravitational physics in intermediate field strength regimes that bridge weak field galactic tests and strong field black hole tests. These observations reveal systematic patterns that could indicate gravitational modifications operating across multiple acceleration scales. The cumulative evidence from these diverse observational anomalies creates a coherent picture, suggesting that gravitational physics operates differently than predicted by general relativity. Plus dark matter models, with systematic patterns that support modifications to gravitational theory rather than exotic matter components that remain undetectable despite extensive searching across multiple experimental approaches and theoretical frameworks. Scale relationships. The mathematical relationships connecting galactic properties across enormous ranges in size, mass, and brightness reveal underlying physical principles that challenge dark matter explanations while supporting theories that modify gravitational physics at specific acceleration scales. These scaling relationships demonstrate remarkable universality that suggests fundamental gravitational modifications rather than the environmental variations expected. If galactic dynamics were dominated by randomly distributed dark matter halos with diverse formation histories and structural properties, the Bryonic-Tully-Fisher relation connects galactic rotation velocity to stellar mass with extraordinary precision across over for orders of magnitude and galaxy brightness, from the faintest dwarf galaxies to the most luminous giant systems. This tight correlation demonstrates that galactic dynamics are determined entirely by visible matter through modified gravitational physics rather than by the dark matter distributions. That should show much greater scatter based on cosmological simulation predictions. The fundamental plane of elliptical galaxies reveals correlations between stellar velocity dispersion, surface brightness, and effective radius that remain constant across cosmic time and diverse environments, suggesting that gravitational physics operates according to universal principles rather than through the environmental effects expected if galaxy properties were determined by dark matter halo assembly histories that vary dramatically between different cosmic locations. The mass discrepancy acceleration relation MDR demonstrates that the ratio between observed gravitational acceleration and that predicted from visible matter depends only on acceleration magnitude, showing identical functional form across all galactic systems regardless of morphology, environment, or evolutionary history. This universality indicates fundamental gravitational modifications, rather than diverse dark matter properties that should create scatter in this relationship. Dwarf galaxy scaling relationships reveal that the smallest galaxies follow the same mathematical relationships as giant systems, extending scaling laws across over 6 orders of magnitude in stellar mass. This scale invariance suggests that galactic dynamics are governed by universal physical principles rather than by dark matter physics that should operate differently in systems with vastly different mass scales and formation mechanisms. The radial acceleration relation R shows that gravitational acceleration from all sources correlates perfectly with acceleration from visible matter alone, with a functional form that matches theoretical predictions from modified gravity theories while contradicting dark matter expectations. This relationship holds for all galactic components, including stars, gas, and different stellar populations, indicating universal gravitational modifications. Central surface brightness relationships demonstrate that galaxy structural properties correlate in ways that reflect underlying gravitational physics rather than dark matter halo properties. The observed correlations between central density, scale length, and total luminosity follow patterns predicted by modified gravity theories while challenging dark matter models that predict much weaker correlations between these observationally distinct quantities. The velocity-mass correlation for galaxy clusters extends galactic scaling relationships to larger scales, showing that cluster dynamics follow similar mathematical principles as individual galaxies despite involving completely different mass scales and physical processes. This scale-independent behavior supports universal gravitational modifications rather than scale-dependent dark matter physics that should operate differently in cluster environments. Satellite galaxy kinematics around central galaxies reveal correlations that extend scaling relationships to galaxy group scales, with satellite velocities and spatial distributions following patterns that correlate with central galaxy properties in ways predicted by modified gravity but not by dark matter models. These correlations suggest that gravitational modifications affect dynamics across multiple scale regimes simultaneously. The stellar mass-halo mass relation inferred from galaxy clustering observations shows systematic deviations from theoretical expectations based on dark matter simulations, with observed relationships requiring gravitational modifications to explain why galaxies populate dark matter halos differently than predicted by structure formation models. These deviations suggest that inferred dark matter properties reflect gravitational modifications rather than actual invisible matter. Gas fraction scaling laws in galaxies reveal that the proportion of gaseous to stellar mass correlates with total gravitational acceleration in ways that reflect modified gravity predictions rather than dark matter expectations. These correlations demonstrate that baryonic physics operates within gravitational potentials determined by visible matter through modified gravitational physics rather than through dark matter dominance. The size-mass relationship for galaxies shows correlations that remain constant across cosmic time and diverse environments, suggesting that galaxy structural properties are determined by universal gravitational principles, rather than by dark matter halo properties that evolve differently in different cosmic environments. These correlations challenge hierarchical assembly models based on dark matter while supporting modified gravity approaches. Globular cluster system properties correlate with host galaxy characteristics in ways that extend scaling relationships to subgalactic scales, demonstrating that gravitational modifications affect structure formation processes across multiple hierarchical levels. These correlations suggest that modified gravity influences both galaxy formation and the formation of their stellar subsystems. The metallicity-luminosity relationship in galaxies reveals correlations between stellar chemical composition and total gravitational potential that reflect baryonic physics. operating in gravitational fields determined by visible matter rather than dark matter. These chemical evolution patterns provide independent evidence for gravitational modifications that affect star formation and stellar nucleosynthesis processes. Spiral galaxy pitch angle correlations demonstrate that disk galaxy morphology relates to gravitational physics in ways that extend scaling relationships to structural properties. The observed correlations between spiral arm geometry and rotation curve properties suggest that galaxy morphology reflects underlying gravitational modifications rather than dark matter halo characteristics. The black hole galaxy relationships reveal correlations between central supermassive black holes and host galaxy properties that challenge dark matter models. While supporting modified gravity theories, these correlations suggest that both galaxy formation and black hole growth operate within gravitational potentials determined by brightnet matter through modified gravitational physics. Intercluster medium properties in galaxy clusters show scaling relationships that extend galactic correlations to cluster scales, with gas temperature and density distributions following patterns that correlate with modified gravity predictions rather than dark matter expectations. These relationships demonstrate that gravitational modifications affect both stellar and gaseous components across cosmic scales. The H-metallicity kinematics relationships in stellar populations reveal correlations that reflect galactic chemical and dynamical evolution operating within gravitational potentials determined by visible matter. These stellar archaeological signatures provide historical evidence for gravitational modifications affecting galaxy evolution over cosmic time rather than dark matter influences. Lensing mass-to-light ratios inferred from gravitational lensing observations show systematic patterns that correlate with modified gravity predictions rather than dark matter expectations. These correlations suggest that gravitational lensing reflects modified gravitational physics rather than invisible matter distributions, providing geometric tests of gravitational theories. The universal acceleration scale that characterizes galactic rotation anomalies appears in multiple independent observational contexts, suggesting a fundamental physical constant related to gravitational modifications rather than environmental effects from dark matter. This universality indicates that galactic dynamics reflect intrinsic gravitational physics rather than extrinsic dark matter properties. Surface density thresholds for star formation in galactic disks correlate with gravitational acceleration in ways that suggest modified gravity affects astrophysical processes. Beyond purely dynamical effects, these correlations demonstrate that gravitational modifications influence baryonic physics including star formation, stellar feedback, and ISM dynamics throughout galactic environments. The consistency of scaling relationships across different galaxy types, environments, and cosmic epochs demonstrates that galactic physics operates according to universal principles that are incompatible with dark matter models predicting environmental variations. Instead, these relationships support modified gravity theories that naturally explain galactic dynamics through fundamental modifications to gravitational physics operating at galactic acceleration scales. These scale relationships collectively demonstrate that galactic physics follows universal mathematical principles that extend across enormous ranges in physical parameters, while maintaining functional forms that match modified gravity predictions. The universality and precision of these relationships provide compelling evidence that galactic dynamics result from modifications to gravitational physics, rather than from invisible matter components that somehow maintain perfect correlations despite having no direct observational evidence for their existence. Laboratory tests. Precision laboratory experiments testing gravitational physics at the acceleration scales characteristic of galactic rotation anomalies have revealed subtle deviations from general relativistic predictions that could support modified gravity theories while challenging dark matter explanations for cosmic structure. These terrestrial tests of gravitational modifications operate in controlled environments where systematic effects can be carefully characterized, and where alternative explanations for observed effects can be systematically eliminated through experimental design and statistical analysis. Torsion balance experiments represent the most sensitive laboratory tests of gravitational physics. Using suspended masses and precision optical interferometry to detect gravitational forces with sensitivity approaching fundamental thermal noise limits. The HeatWash group at the University of Washington has achieved precision in gravitational measurements exceeding 1 part in 1013, enabling tests of gravitational modifications at acceleration scales relevant to galactic dynamics and dark matter alternatives. The equivalence principle, which underlies general relativity by stating that gravitational and inertial masses are identical, has been tested using rotating torsion balances that can detect violations indicating new gravitational physics. These experiments compare the gravitational acceleration of different materials toward Earth and other massive bodies, achieving precision sufficient to detect violations that would indicate modifications to gravitational physics beyond Einstein's theory. Inverse square law tests using laboratory masses separated by distances ranging from micrometers to meters provide direct measurements of gravitational force scaling that can reveal departures from Newton's gravitational law at short distances. These experiments have achieved sensitivity to detect extra-dimensional gravity effects and other modifications predicted by alternative theories, while maintaining consistency with general relativity within measurement uncertainties. Atomic interferometry experiments use quantum mechanical superposition of atomic wave functions to create extraordinarily sensitive gravimeters capable of detecting gravitational acceleration changes smaller than 1 part in key. These quantum sensors can measure gravitational effects with precision approaching fundamental limits imposed by atomic physics and quantum mechanics, while providing model-independent tests of gravitational modifications. The Lunar Laser Ranging Experiment measures the distance between Earth and retroreflectors placed on the Moon by Apollo missions with centimeter precision, enabling tests of general relativity and gravitational modifications through analysis of lunar orbital dynamics. Decades of ranging observations have confirmed general relativistic predictions, while constraining alternative gravity theories through their predictions for orbital evolution. Satellite-based tests of gravitational physics using GPS satellites and dedicated gravity missions provide precision measurements of gravitational effects in weak field regimes that complement laboratory experiments. The GRACE mission and its successor GRACE-FO measure Earth's gravitational field variations with unprecedented precision, enabling tests of gravitational modifications while monitoring global climate and geological processes. Gyroscope precession experiments test frame dragging effects predicted by general relativity using ultra-precise gyroscopes in Earth orbit, providing measurements of space-time geometry modifications caused by Earth's rotation. Gravity Probe B achieved the required precision to confirm frame dragging effects while constraining alternative theories that predict different precession patterns for spinning objects in gravitational fields. Clock comparison experiments using atomic clocks at different altitudes test gravitational redshift predictions from general relativity with extraordinary precision, achieving accuracy sufficient to detect modifications to gravitational time dilation at the level predicted by some alternative gravity theories. These tests compare clock rates between satellites and ground stations while controlling for non-gravitational systematic effects. Pendulum experiments in deep underground laboratories test gravitational physics in environments shielded from seismic noise and atmospheric effects, enabling precision measurements of gravitational acceleration and its variation with position. These experiments can detect anomalous gravitational effects while controlling for environmental systematic effects through careful experimental design and multiple measurement techniques. The microscope mission tested the equivalence principle in space using free-falling test masses in precisely controlled orbits, achieving sensitivity to equivalence principle violations approaching 1 part in 1015. This space-based experiment avoided many systematic effects that limit ground-based equivalence principle tests while providing constraints on gravitational modifications that could explain galactic dynamics. Cavity resonator experiments test for modifications to electromagnetic field propagation and gravitational fields by measuring changes in electromagnetic resonance frequencies. Caused by gravitational effects, these experiments can detect violations of local Lorentz invariance and other departures from standard physics that might indicate modifications to fundamental physical laws underlying gravitational phenomena. Molecular interferometry experiments use interference patterns created by molecular beams to test gravitational effects on matter waves, providing quantum mechanical tests of gravitational physics with sensitivity to detect modifications predicted by alternative gravity theories. These experiments explore the interface between quantum mechanics and gravitational physics while testing fundamental assumptions about matter-gravity interactions. The fifth force searches use laboratory experiments designed to detect additional fundamental interactions beyond the known electromagnetic, weak nuclear, strong nuclear, and gravitational forces. These experiments test for short-range modifications to gravitational physics that could indicate extra-dimensional effects or other departures from standard gravitational theory predicted by alternative cosmological models. Precision measurements of the gravitational constant G using different experimental techniques provide tests of gravitational physics through comparison of results obtained using different measurement methods. Systematic discrepancies between different G measurements could indicate modifications to gravitational physics or experimental systematic effects that require resolution through improved measurement techniques. Superconducting gravimeter networks provide continuous monitoring of gravitational acceleration variations with sensitivity sufficient to detect subtle modifications to gravitational physics. Operating at specific acceleration scales, these instruments can measure gravitational effects while controlling for environmental systematic effects through correlation, analysis, and comparison between multiple measurement sites. Laboratory tests of gravitational redshift use precision spectroscopy to measure frequency changes of electromagnetic radiation in Earth's gravitational field, providing direct tests of gravitational time dilation with accuracy sufficient to constrain modifications to general relativity. These experiments compare atomic transition frequencies at different gravitational potentials while controlling for non-gravitational systematic effects. Magnetic levitation experiments test gravitational effects on diamagnetic materials suspended in magnetic fields, providing measurements of gravitational acceleration while eliminating many systematic effects associated with mechanical support systems. These experiments can achieve high precision in gravitational measurements while testing for anomalous gravitational effects on different types of matter. The Large Hadron Collider provides indirect tests of gravitational modifications through precision measurements of particle physics processes that could be affected by extra-dimensional gravity or other modifications to fundamental physics, while primarily designed for particle physics research. The LHC can constrain gravitational modifications through their predicted effects on high-energy particle interactions. Future laboratory experiments proposed for testing gravitational modifications include space-based missions using ultra-cold atoms, optical clock networks with improved precision, and dedicated tests of gravitational physics using quantum sensing technologies. These next-generation experiments will achieve sensitivity levels that could definitively test predictions from modified gravity theories while exploring new regimes of gravitational physics. The integration of multiple laboratory test results provides comprehensive constraints on gravitational modifications that complement astronomical observations of galactic dynamics and cosmic structure, while individual experiments may not achieve sensitivity sufficient to detect gravitational modifications at galactic acceleration scales. The combination of multiple experimental approaches provides increasingly stringent tests of alternative gravity theories. The absence of confirmed gravitational modifications in laboratory tests creates tension with astronomical observations suggesting gravitational modifications at galactic scales, indicating either that gravitational modifications operate only in specific environmental conditions or that alternative explanations for galactic dynamics may be required. This tension motivates continued precision testing of gravitational physics using improved experimental techniques and novel measurement approaches.